let's ask some questions. Suppose we have a V that is a non-zero subspace of Rm, and the dimension of V is known to be K. S is a subset of V, and S has raw vectors. Suppose we know that S is linearly independent. S is linearly independent and has raw vectors, and subspace V has dimension equal to K. Can we conclude from here raw and K, raw smaller or equal to K, or raw larger or equal to K? Pause and think about this. Remember, the basis for V has K vectors, and a basis is a linearly independent subset that is as large as possible, and a basis for V has K vectors. So if S is linearly independent, it cannot have more than K vectors, right? So rho must be smaller or equal to K. This is the result of theorem 4.6. Another question. Suppose S is linearly independent and the number of vectors in S is equal to K. So a linearly independent subset with K vectors. Can we conclude from here that S is a basis? Pause and think about this. What do you think? Is it a basis? Let's try to use one of the theorem to get our point. S is linearly independent, so a useful theorem, this would be extension theorem. S is linearly independent. By extension theorem, S can be extended to a basis S prime, and S prime has K vectors. And S has K vectors as well. So we can conclude that S is the same as S prime, and S is a basis. A related question. Suppose S is a generating set for V, and S has K vectors, a generating set with K vector. Does that mean S is a basis? Pause and think about it. S is a generating set, right? So a theorem that might be useful in this case would be the reduction theorem. S is a generating set, so by reduction theorem, some subset S prime of S, we remove some vectors and we get a subset S prime. So S prime is a basis, and because it's a basis, it has K vectors, because K is the dimension of the subspace. So we can conclude that S and S prime are the same set, and S is a basis. Theorem 4.7 gives a summary of what we have just discussed. Suppose V is a non-zero subspace of Rm, and the dimension of V is equal to K. S is a subset of V with K vectors, the same as the dimension of K. Then S is a basis for V if either S is linearly independent or S generates V. Remember, a basis for V is a linearly independent generating set. So before, when we want to show that a set is a basis, we need to show two things. First, it's linearly independent. Secondly, it's a generating set. But according to the theorem, there's an alternative way to this. If we start from a set with K vectors, it's sufficient to show that it's linearly independent to show that it's a basis. Or we can do this. Again, starting from a set with the K vectors, if we can show that it's a generating set, then it is a basis. We do not need to show that it's linearly independent, it's a generating set. Using the theorem, now we can show that a set beta is a basis for a subspace V of Rm using the following three steps. First of all, it's a subset of V. Secondly, the number of vectors in beta is the same as dimension of V. The last one, this or this. Only one of them is enough. Beta is linearly independent, or beta is a generating set for V. Let's look at an example. Suppose we have a 4x4 matrix A here, and W is the column space of A, and we have a beta with 3 vectors. We would like to know if beta is a basis for the column space of A. According to what we have just discussed, we can show that beta is a basis for W if beta satisfies all 3 conditions. The answers to all these 3 questions are yes. First of all, beta is a subset of column space of A. 2, beta linearly independent, or beta is a generating set for W. 3, the number of vectors in beta is the same as the dimension of the column space of A. Beta has 3 vectors, so that's the same as asking whether dimension of column space of A is equal to 3. The first one, is beta a subset of column space of A? This is the same as asking if each vector in beta is a linear combination of the columns of A. And we know how to answer this question, right? We need to check if the system of linear equation AX equal to B is consistent for each vector in beta. And we can use the method in chapter 1 to verify that this is indeed true. Now the second one, is B linearly independent? How can we determine whether B is linearly independent or not? There are a number of equivalent conditions that we have stated earlier. For example, we can form a matrix B that consists of the vectors in beta, 3 vectors, and we can check if the rank of B matrix is the same as the number of column vectors. So is rank B equal to 3? We compute the reduced row echelon form of B, and we find out that the rank of B is indeed 3. So yes, B is linearly independent. Last one, we want to find out if the dimension of column space of A is equal to 3, the same as the number of vectors in beta. How can we find out the dimension of a particular space? We find a basis, and we count the number of vectors in the basis. How can we find a basis for column space of A? We know the pivot columns form a basis for column space of A. So we find the reduced row echelon form, and we find out how many pivot columns there are. There are 1, 2, and 3. There are 3 pivot columns. So the dimension of the column space of A is indeed equal to 3. So there we go. Beta is indeed a basis for column space of A. This one should be W.